So they decrypt. And we'll write that we obtain PR by decrypting. What's the key we use to decrypt? KAB is just shared secret key. B receives a message from A, therefore we use KAB to decrypt. And they decrypt what they receive, and they get some value PR, the plain text received. In this case, we'll assume that there's no attacker in the middle at this stage. So CT and CR are the same. That is CT equal to CR? Yes, in this case. Later we'll see no. Just for this initial case, they're the same. So we could have written this equation instead of CR, PR, CT. Does PR equals PT? Does PR, the plain text received, equal the plain text transmitted? Yes. Why? Let's look at our assumptions. Yes, I think it's obvious, but let's make sure that our assumptions capture that. Decrypting the ciphertext with, so assumption A6 on this list, the one at the bottom, decrypting the ciphertext with the correct key, the same key that was used for encryption, will produce the original plaintext. So that's the assumption that tells us that yes, the plaintext received will be the same as the plaintext transmitted. Our assumption, if we use the correct key, and we can see KAB was used to encrypt, KAB, the same key is used to decrypt. Decrypt CR, which is actually the same as CT, we will get PR being the same as PT. We assume that's the case. Let's look at this case. We get the same plaintext back. So B gets the plaintext. What if? I don't know, we'll see that in a moment. Let's see an attack. From confidentiality perspective, we now have a malicious user. And the malicious user in the middle, instead of C calling C, we'll call him Mao, the malicious user. Okay. Now, the malicious user, what do they know in this case? The attacker? Well, the things that they know. Let's have a look at this list of assumptions. If you scroll down the assumptions, we talk about what the attacker knows. That's on one of the slides as well. We assume that the attacker knows all the algorithms used. So they know what was used for encrypting and decrypting, whether it was DES, AES, or something else. We assume that the attacker can intercept any message. A message was sent across the network. The attacker can get a copy of that message. They know C, CT, or CR. They're the same in this case. The attacker does not know the secret values. In our case, they do not know KB. False attacks, unless the length of the key is less than, I'll put a number here, less than about 80 bits. Now that's not precise, but assuming the key is long enough, they will not be able to do a brute force attack and discover the key. So the attacker knows the algorithms, they know the ciphertext, but they don't know the key. The malicious user in this case, let's say CT, what was transmitted, it's also the same as CR. They know the encryption algorithm. The encryption algorithm. They want to find the plain text or the key. They can't guess the key because it's the length such that they can't do a brute force attack. So what do they try to do? To get the plain text. What the attacker can try to do is decrypt using some key. CR.
背景センターではそんなネームプレートを僕制作電気上をやってはる反動不足で掲載はこちらポイントとなりますそうですね開催中になっておりますそのさんがこれ僕どねこれは
So if we decrypt the ciphertext using some key other than KAB, we get some plain text. The plain text the malicious user gets. The question is the plain text the malicious user gets the same as the transmitted plain text? What's the answer? They decrypted the ciphertext using the key that they chose. The key that they chose is not the same as KAB, and they get some plain text as output. They apply the function, they get an output. Some plain text understood is the plain text the malicious user gets. Is that value the same as what A started is? No, it's not, and that's one of our assumptions. A7. Decrypting ciphertext using the incorrect key will not produce the original plaintext. Okay, so we've used a different key, therefore we assume we will never get the same plaintext. Malicious users will be able to recognize that this is wrong. They know that it's not the right plaintext, but that's of no use to them. They want to get the correct one. No, it is not. Okay. This is just showing that we've achieved confidentiality. We've sent a message from A to B. B decrypted and got the original plaintext because they have the key. The malicious user that intercepts that ciphertext, even if they try to decrypt, they cannot get the original plaintext because they don't have the key. So that's the concept. Just showing how we apply those assumptions to show that that's true. Any questions on confidentiality? What does the attacker need to do to find the plaintext? Again, two copies. Two copies of what? In this case, we assume the malicious user only knew the current ciphertext and the algorithms. maybe the malicious user has observed past communications and have seen past pairs of past ciphertext messages, different ones, and somehow have managed to learn the corresponding plaintext values. And that's a common assumption in practical attacks, that the attacker, so this is a slight extension, the malicious user also knows pairs. Like they know that in the past there was some ciphertext, some old ciphertext that was sent from A to B. They know it was encrypted with the same key, and they have also somehow discovered the corresponding plaintext. This is what we say is a plaintext ciphertext pair. It's easy to get the old ciphertext when you intercept many messages. But how do they get the old plaintext message? And they don't know the key. Maybe the message was released through some other means. Maybe the message was old and was no longer needed to be kept secret. So therefore it was not public, and the attacker knows about that. Therefore the attacker now knows an old ciphertext value, an old corresponding plaintext value. They don't know the key to get from one to the other, but they know the pair. They could try to use that to help them find the key so that they can decrypt the new ciphertext value they've intercepted. So practical attacks may use past values to try and help. The secure algorithms, it still doesn't make it easy to find the key or decrypt the ciphertext. So for AES, for example, there are not attacks. Even if you have billions of past pairs of plaintext and ciphertext, it still doesn't help you to get back to the original. So no, that doesn't help. The assumer does not help. Even if you know these many billions of them. Service. Well, there's nothing they can do under the assumptions that we work. Assuming they can't find the key, we assume that there's one shows a key KAB which is not already. So the only way they're terrified is to guess it. And we know that it will take too long to try and guess that. So they can't find the key. Assuming the algorithm, the algorithms are strong, there are no flaws in the AES is considered like that, then there's no way for the attacker to find the plaintext messages. And that gives us an advantage. That's why we consider this concept secure. If we send a message from A to B and someone in the middle changes it along the way, can the receiver detect that that change was made? If they can detect the change was made, then we can maintain integrity. If a change can be made without the receiver knowing a change was made, then that's a compromise of the integrity of the data. Authentication is about if someone sends us a message pretending to be A, but they're actually the malicious user, and we think it's from A, then that defeats the authentication service. We want to be able to be sure the message came from A, not someone pretending to be A. So we'll look at how encryption provides those services as well. So we'll look at some variations on this where the malicious user doesn't just intercept the message, but they may intercept and modify the message. And we'll try to see if the malicious user can modify the message without the detecting that it was modified. If they can, then that attack is successful. Let's go through some scenarios. Which is obtained by encrypting with KAB. We're sending from A to B still, the plaintext, and we transmit that. We transmit CT. Now, let's have the malicious user intercept this message before it gets to B, not just let it go through, but intercept it and try to make a change to that message, with the hope of sending a message onto B that B thinks it's the original message from A, but it's in fact a modified message. Let's see if that's possible. So what happens now is the malicious user gets a copy. What can they do when they receive CT? Can they read the plaintext? Can the malicious user read the plaintext when they get the ciphertext? No, we just saw in the previous case they cannot. It's encrypted, they cannot read the plaintext. But they could try to make up some different plaintext and encrypt that and forward it on to B with the hope that B thinks that was the message from A. Let's try that and see what attack may be possible. Let's say that the malicious user gets this ciphertext and modifies it first. And send the modified version onto the user B. That is, the modified one I'll denote as CT prime. And mark on the top prime, just to say that they've changed the ciphertext. Maybe the ciphertext was a million bits, they changed some of those bits to try to perform an attack. Let's see what happens. Where CT prime is different from CT. Different values. We send it on to B. B receives some ciphertext. I'll denote that as CR. From B's perspective, it's received some bits, some ciphertext. What does B do next? Decrypt. Alright, you receive ciphertext, you decrypt. You decrypt what you receive. Decrypt using a key, CR, and we'll get some value. I'll denote as PR. What key do I use to decrypt? KAB. I received a message from A. I think it's from A. The from message, the from field in the message says A. I am B, so I use key KAB. what happens at B now? It gets the wrong plaintext, or it gets recognisably wrong plaintext. That assumption is which number? It's maybe not captured here directly, but it's based upon A7. If we use the wrong key, we'll get... Well, it's a variation of A7 here, as if we're using a different key, or in fact was a different ciphertext, we'll get the wrong, recognisably wrong plaintext, because CR is the same as CT prime. CT prime is different from CT. Okay, we're trying to decrypt the wrong ciphertext here. So we're going to get some plaintext that is different from PT and recognisably wrong. So what will happen? B recognises that the plaintext that they get from that decryption is wrong. It's just random characters. They expect some English message or some structured message. They decrypt it using a key, some ciphertext, which was not obtained from an original structured plaintext. It was a different one. So B recognises that PR is wrong. So I think the assumptions we've got, we really should have another one that is a variation of A7, is that it's slightly different. Here we say decrypting with the wrong key, but in the same way, if you decrypt different ciphertext, the wrong ciphertext, you will not get you'll get a different plaintext. Decrypting two different ciphertexts will give two different plaintexts if you use the same key. Because CR is different from CT. B recognises the plaintext is wrong, it looks like random characters, it's not a structured message, and therefore has detected something's gone wrong. They don't trust the plaintext and discard it. So that's a case where the attack, the malicious user tried to modify something, is detected. We don't know how they modified it, but we know something went wrong, so we discard what we received. We don't trust it. We'll try some variations. What could the malicious user try to do such that B doesn't detect that? There are a couple of other choices. What could you try? Today's your chance to put on your malicious hat, your black hat. Try to do some bad things. What could you try to do as a malicious user so that B doesn't detect a change? Changed what? We could try to change the plaintext. That's effectively what we did there. If we modify something here, let's say we choose a new plaintext, encrypt that with a key, the key of the malicious user, and send them ciphertext on to B. Similar issue as before. If we have a new plaintext by the malicious user, then the key that was used to encrypt cannot be KAB. So the application of these assumptions is to apply them, or to use the logic to see how they can be used to provide the services. Malicious user, they choose some new plaintext, PT prime, different plaintext. They want to say this plaintext was decrease the malicious user's salary by 10,000 bucks. They change it to increase, so they try to have a new plaintext and try to fool B into getting that. They choose a new plaintext and they encrypt that new plaintext with a key and get a new ciphertext. What key do they use? Or maybe an easier question, what key do they not use? They cannot use KAB. They can use some other key, we'll denote as key of the malicious user, but it's not KAB because they don't know that. They get some ciphertext. And because it's a different key, we'll assume that the ciphertexts are not the same. CT is not the same as CT prime. We send that on. And as we send CT prime, user B receives that. They receive CR, which is in fact the same as CT prime. They receive that and try to decrypt. What key do we use to decrypt at user B? KAB. We still think it's from A. When we decrypt CR, well, in fact, it's the same as CT prime. We could rewrite that as decrypting with KAB. CT prime, the different ciphertext. Here, CT prime was obtained by encrypting plaintext with K of the malicious user. Here we try to decrypt with the incorrect key. Encrypted using K of the malicious user. We try to decrypt with a different key. Our assumption in A7 says if you try to decrypt with the incorrect key, you will get the wrong plaintext and it will be recognised as wrong. Okay, B gets plaintext. PR. I say PR as well. Attack detected. If we get plaintext that doesn't make sense, then we detect that something's gone wrong. We don't care what specifically went wrong, but something's gone wrong and don't trust the message. So the use of encryption not just provides confidentiality, but also provides protection against modification attacks. This is the attacker trying to modify the data. And it provides the data integrity service. Data integrity is that if something's modified, we can detect that. And that's what's happening here. The previous case was one where they just tried to modify the ciphertext. This is effectively the same. They produce a new ciphertext. B detects that because we're using a different key to decrypt. Is there anything else a malicious user could try to do without knowing KAB? I think if you try to consider all the scenarios, you will not find one where they can fool B, because B will always detect. They need KAB. If they want to modify something, they could choose a new plaintext. If they did have KAB, then they could fool B into getting a message, but they don't is, let's try to do a masquerade attack. The malicious user will pretend to be A. We've got user B. Start again. User B, there is no user A here. We'll start with just a malicious user. What they do is they send a message to user B. They choose their own plain text message. Let's just call it P. They encrypt that with a key and get some ciphertext and send the ciphertext to user B. But they say that this message is from A. What key do they use? Let's make some more space. Sorry. What key are they going to use to encrypt? The malicious user is going to use KAB. How? They don't know KAB. User A knows, so we're not user A here, we're a different user. User A knows KAB, user B knows KAB, but the malicious user does not. But they want to pretend to be A.